Solutions Podcast. This is Mr. Saari. We're going to start out with identifying some conic sections. Before we begin that, let's go over how do we identify conic sections when they are in this polynomial form without any perfect squares built in. So, how do we do it? Well, first of all, the easiest one to identify are parabolas. Parabolas, as we remember, only have one of either x or y squared. So only one of x and y squared. So if we scan through these and look at which one only has one term squared, we see that it's this one right here. Only y is squared. So B must be a parabola. Doesn't matter about signs or anything like that. We just look at what's squared. Okay, next. Now, next, how to determine between circles, between ellipses, and among hyperbolas. Okay. Well, the defining feature of hyperbolas is that you have one of x and y. So both are squared for all of these. So both squared for all of these. So x and y are both squared. So you need squared terms for both of those. But for hyperbolas, you have one positive and one negative out of the x squared and y squared. So you're looking for x squared and y squared, but you got one positive and one negative for hyperbolas. So we scan through these and we see that this one right here has your one positive and one negative squared term. So that one must be our hyperbola. Has nothing to do with what the coefficients are. Remember, the coefficients end up creating different radii in the x and y direction. Either the a and b, if you're talking about that, or rx and ry as we referred to them in class. That's our hyperbola. All right, next, our ellipse. So ellipses versus circles, they're going to have the same sign. Usually they're both positive, both x squared and y squared are positive, but they could both be negative, hypothetically or theoretically. But the key is for circles, circles have the same coefficient for x and y, while ellipses have different coefficients for x and y. So you have different coefficients for ellipses. Remember, coefficients, that's the number in front of the x squared and y squared. So you have different coefficients for ellipses. Notice how the x squared and y squared have different coefficients here. So that makes this the ellipse. Whereas this one, x squared and y squared, doesn't have to be 1 for each, but this one happened to be 1. So 1 for each, same coefficient. So that gives us our circle. And there we have it. All right, so now we're finding the standard form of an equation of the circle with a center at negative 3, 5, and a point on the circle of negative 2, 1. Okay, so recall our formula for circles, which is here at the end. We have x minus h squared plus y minus k squared equals r squared. So I'm just going to copy that in. So we've got x minus h squared plus y minus k squared equals r squared. Okay. So of the things we know, center at negative 3, 5. So center at negative 3, 5 tells us our h and k. Remember, they're the opposites of these points. And a point on the circle, remember, if you're given a point on a curve or a line, that represents an x and a y. So we've got h and k. We know h, so this is going to end up being positive 3. This is negative 5. And we've got x and y. So I'm just going to plug this one in first. So we've got x plus 3 squared y minus 5 squared equals r squared. And again, we don't know, we would be, if we knew the radius, and then we are finished. So now we just have to find the radius and then plug that into this equation, and we're good to go. So now we're going to plug in our x and y in for the x and y, so that allows us to solve for r. So I've got negative 2 plus 3 squared, just again substituting in for x and y in this equation, plus 1 minus 5 squared equals r squared. So now we can simplify and solve for r. So it's going to be 1 squared, which is 1, plus negative 4 squared, which is 16, equals r squared. So I get 17 equals r squared. Now, of course, I could solve for r. It didn't ask for me to find that. All I need is the standard equation. Well, now I know r squared is 17. I can just say, all right, 17 equals x plus 3 squared plus y minus 5 squared equals 17. And there we go. And that gives us our standard form of the equation of the circle. Now, I didn't solve for r because we wanted r squared, but had you solved for r, you would have ended up with the square root of 17. All right. Okay, standard form of the parabola with a focus on negative 4, 3 and directrix at x equals negative 8. Okay, so quick reminder, just grabbing these from the end of the review. So our parabola, up, down versus left, right. Notice how in our up, down version of the parabola, the x is the squared term, and we go up and down from the y coordinate to our focus. And then if we had a left-right version of the parabola, that would just mean y was squared. So we look at these two equations, and we see, and we basically just need to figure out where we're at here. Okay. So always good to draw a sketch when you're working with one of these. So our focus is at negative 4, 3. So negative 1, 2, 3, 4, 1, 2, 3. So there's our focus. Call that point F. And directrix of x equals negative 8. So we can go 4 more over here. 1, 2, 3, 4 more. So there's our directrix. Yeah, that's a line, x equals negative 8 being a vertical line. So if you remember what a parabola looks like, a parabola has the vertex, which is like its center, the center point of the parabola, in the middle of the focus and the directrix. So we know our center point has to be, this is 4 units total, so I go 2 to the left. So my vertex is at, instead of negative 4, 3, it's at negative 6, 3, which that's how I can get my h and k. And I know this is a sideways parabola like this, because that's what the definition of a parabola is. From the vertex here to the focus, our parabola curves around the focus. And the final thing we need to be able to come up with this is this distance. Because this distance right here, that's p. So I know, because that was 2, that p is positive 2. Because remember, that distance from vertex to focus, if it goes either left or right, that means that the y is squared. So we know y is the one that's squared. Y must be the one that's squared because we're a left-right parabola. And because I went right from vertex to focus, that must mean that P is greater than 0. So I'm using my formula where I've got 4P x minus h equals y minus k squared. So I know P is positive 2, so that's going to make this 8, 4 times 2. And then x minus h, I do x plus 6 because that's what the x-coordinate of that vertex was. And then I got y minus 3 squared. And there we go. So there's the standard form of the parabola with a focus of negative 4, 3, and a direction of x equals negative 8. All right, find the standard form of the equation of the ellipse with vertices of 2, 4, and 2, negative 6, and a minor axis of length 4. Okay. All right, so remember, minor axis, that's the shorter one. And the longer, so it's the shorter one, whereas the vertices here, those are the endpoints of the major axis. So the longer of our two axes of the ellipse. So what I mean by this, remember, if you have an ellipse like this, then here are your vertices, and that's the major axis, the length of it. Whereas if you had an ellipse like this, these would be your vertices, and that's the length of the major axis. So you got your minor and your major. So again, minor and your major. So just a quick refresher there. Okay, so let's sketch it out. All right. All right, so vertices of 2, 4, so 1, 2, so 2, 4, and 2, negative 6. So 2, 4, and then 2, negative 6. 1, 2, 3, 4, 5, 6. All right, so we see that it goes from 4 to negative 6. So that major axis is 10 units long. So major is 10 units long. And again, remember, the radius is half that. So if we just go 5 from in the middle, 5 towards the middle, and that gives us our center. So we got our center at the midpoint of those 2 points. So down 5 gets us to 2, negative 1. 2, negative 1. Our minor axis we already know is 4. So if the minor axis is 4, then we got to go left and right a certain amount to make an axis length of 4. Well, to make an axis length of 4, I need to go 2 each way. So 1, 2, 1, 2. So there's my minor axis. And recall, remember, this is my Rx, my radius in the x direction. This right here is my radius in the y. And remember, those are formula for an ellipse. X minus h squared over Rx squared plus y minus k squared over Ry squared equals 1. And again, you could call these A and B as well, but we call them in class Rx and Ry, because remember, they're the radius in each direction squared. All right, so I know my radii. My Rx is 2, my Ry is 5, and my center is at 2, negative 1. So now I've got everything I need to write the standard form of the equation. So x minus 2 squared plus, I've got y plus 1 squared. So there's my center and how it manifests itself in the equation. Now I just need Rx squared, which remember Rx is 2. So that means this is 2 squared, or 4. And then Ry is 5. And this is Ry squared, which is 25. And there we go. And there's our standard equation of our ellipse. Okay. So find the standard form of the equation of the hyperbola with vertices 0, 1, and 0, negative 1, and foci 0, 4, and 0, negative 4. Okay. So remember, and just connecting back, remember our foci for our, if we had, well, we have foci, but we didn't need them for this ellipse. Remember the foci go a certain distance. It's kind of like you have this focal length, which we called L in class. On the formula sheet below, they're referred to as C. So L is the distance, or that C is the distance from the center to each focus along the major axis. And remember, it's always either b squared plus c squared equals a squared. But the way that we worked with this in class was it was the smaller of rx or ry. So we'll say rx for this case. Rx squared plus L squared equals Ry squared. Where this could be Rx or Ry, they're interchangeable, but this is the smaller one of those two, and this was the bigger of those two. And L is just along for the ride there. So that's how we could find the focus of an ellipse. Focus for a hyperbola is different in that the focal length for the hyperbola is always the greatest of Rx, Ry, and L. And they still have that Pythagorean relationship. So we know in an ellipse, it's Rx squared plus Ry squared equals L squared. And remember, L, the focus goes in the same direction as the positive term. That's positive of x squared and y squared, because remember, only one will be positive. So it goes in that same direction. Okay, so let's find it. All right, so I have vertices of 0, 1, and 0, negative 1. So they're my vertices. So I know, because those are called my vertices, I know my foci are in the same direction. But again, we were told it was in that direction, so we didn't need them. So 1, 2, 3, 4. So there's my foci, and 1, 2, 3, 4. So there's my other focus. And what I need to do now is use the information that these are the foci and these are my vertices to find where my other point is. Okay, so I know I have Rx. This distance right here is Rx. My center's at 0, 0. It's always at the midpoint of the vertices or midpoint of the two foci for ellipses and hyperbolas. So my center's 0, 0. I know because my foci go vertically and my vertices go vertically as well, for the y direction. I know that y has to be squared, or sorry, y squared is the positive term, so y squared is positive, so x squared is negative. So in the center 0, 0, so I know it's just going to be y squared over something minus x squared over something equals 1. That's what we've got here. Okay? And remember, this is still ry squared, and this is still rx squared. So I just need to know what ry and rx are. Well, I've got ry. Ry is this distance from center to vertex. So that's just ry equals 1. So 1 squared is going to be y squared over 1. You could just write it as y squared. I like to write out y squared over 1 though. So now we got to find rx, and then we'll be finished. So the radius in the x direction, remember, we use this relationship here, this Pythagorean relationship, because we know 2 of the 3. We know L is 4, the distance from center to focus. So again, this distance right here, that's our focal length. That's L, which is 4. Again, you could also think of it as C, right? On the formula sheet, it's referred to as C. So we've got essentially this equation. We've got 1 squared plus ry squared equals c squared. So we solve this. 1 plus ry squared equals 16. So ry ends up being the square root of 15. Okay, so that would be almost going 4 left and right. So if we plotted those points to be something like this. And then, of course, we would make the box, make our asymptotes go through the corners of the box. And again, I'm doing this not because you have to for this problem, but just as a review of this concept of what parabolas, of what hyperbolas look like. And then we make these parabola-looking curves that follow these asymptotes that start at our vertices, that are centered at our vertices. You can think of it as and curve around our foci. And there we go. And that's how we create this parabola, these hyperbolas. But again, remember, we needed Rx, or we needed Ry, excuse me. No, we needed Rx. I made a mistake over here. I plugged in the 1 for the Rx when I should have plugged in for the Ry. But it's ultimately the same thing. I just mislabeled this as Ry rather than Rx. We already knew Ry was 1, so we found Rx was root 15. So now we just go back and plug it in. And square root of 15 squared is going to be 15. So we got x squared over 15 equals 1. So again, we did not need this whole picture, but I included it because it's good to review how it would be when you're solving. All right, next. Okay, now we're identifying each of the following conic sections and putting them into standard form. Now, again, we can use these same examples up here, and how we tell what if something's a circle, ellipse, hyperbola, or parabola. So again, circles and ellipses, same coefficients for circles, different coefficients for ellipses. Again, different coefficients and same sign, whereas hyperbolas, they could be the same or different coefficients, but have different signs. That's the key for hyperbolas. For all three of these, both x squared and y squared. And then you have, for parabolas, only one of x and y squared. So if we look at number 6 here, we see that both, so we've got x squared and y squared, so it's not a parabola. And they're different coefficients, and they're not opposite signs. So we know this must be an ellipse. This is an ellipse. And now we just have to complete the square to put it in standard form. All right, what do we mean by complete the square? Well, we have to get it so this looks like x something squared over something plus y something squared over something equals 1. So that's what we have to do. So our first goal is to get perfect square trinomials that we can then factor into x something squared. So I've got 4x squared and 24x that are already nice in that order for me. So the first thing I need to do, because there's a coefficient here, I need to factor that out. So I'm factoring the 4 out of the 4x squared plus 24x. So we got 4 times x squared plus 6x. And I know this, if I factored this now, it wouldn't factor into 2 of the same thing. So I got to put a number here so that it does do that. Okay, so I'm going to do that. But again, if I do it on the left side, if I add something to the left side, I got to add something to the right side as well. So on the right side, I'm going to have to add whatever I put right here. Whatever I add to the left, got to add to the right. And something I did not do to begin with, what we normally do is subtract this 45 over. So let's go ahead and subtract that 45 over. So I've got negative 45 over here on the right side. And now we're ready to go with the rest of this. Okay. So I'm going to do the same thing with the y's. I have to complete the square with those two because it's got to be a perfect square. This y squared minus 10y is not. But it's going to be soon after I pick some number that's going to make this factor to that perfect square I want. But again, I added to the left side, so I got to add to the right side as well. So just preparing to, this is just my setup. All right, so we'll do this y squared one first. So again, we wanted to factor into 2 of the same thing. Well, remember, those 2 numbers have to add the negative 10 and multiply to this number by our factoring rules, right? So we know the only two numbers that add to negative 10 that are the same number, which will allow us to write it as y minus 5 squared, are negative 5 and negative 5. So that's why it factors into the y minus 5 squared every time when you're completing the square if this is a negative 10. But in order for that to happen, we have to make this a 25, the multiplication of negative 5 and negative 5. So I say add 25 to each side. Okay, so that gets us to y minus 5 squared for this purplish polynomial. All right, now I got to do the same thing for this blue polynomial over here, x squared plus 6x plus blank. Again, I need two numbers that add to 6 that multiply to the product of those two numbers. So remember, it's x plus 3 and x plus 3. And this 4, don't forget, is along for the ride. So I've got 4 times x plus 3 squared. But in order for that to happen, this has to be the product of 3 and 3, which is 9. It's just simple factoring. So x squared plus 6x plus 9. So you might be thinking to put a 9 here, but remember, I put a 9 inside of a parentheses that was multiplied by 4. So really I added 36 to the left side, 4 times 9. So I'm going to write a 36 right there. And there we are. So now I can combine like terms. So I've got 4 times x plus 3 squared plus y minus 5 squared equals negative 45 plus 25, which is negative 20, plus 36, which gets me to 16. Okay, so we're nearly to this form that we're looking for. But you might notice that we want a 1 over here when it's really a 16. And then we want denominators over here where we don't have those yet. So the way that we can make that happen is by dividing everything by 16. So we divide everything by 16 and then reduce our coefficients over here. So 4 over 16 becomes just a 4 in the denominator. And this is x plus 3 squared. And then we didn't have anything to reduce with, so the 16 just remains in the denominator down there. And we've got y minus 5 squared. And now we are totally set. That is our standard form of our conic section. And we identified it as an ellipse. All right, next. We've got number 7 here. So we've got y squared minus 8x plus 4y plus 28 equals 0. So we've got only one term is squared. So we know it's a parabola, which I've jokingly referred to as parabolas. Parabola. Okay, so y is squared. So I know I end up wanting it looking like this. So I want the y squared by itself on one side, and I want my 4p and my x on this right side. And again, it doesn't matter. Normally they're on opposite sides in our standard equation, but for the purposes, it doesn't matter which side they're on. And my y squared is already on the left side, so I'm just going to leave my y terms on the left side. So first thing we want to do, so this is what we want. So first thing we want to do, I'm just going to work it right over here, is write all my y terms on the left, everything else on the right. So I've got y squared plus 4y on the left side of the equation. And on the right, I've got, well, I want to move 8x and 28 over there, so I'm going to add 8x to each side and subtract 28 from each side. So I've got 8x minus 28 on the right side. Okay, and now in order to make this look like y something squared, I have to complete the square. So let's complete the square. We want to add something to each side to make this thing factor into a y plus or minus something squared. And we know that 2 and 2 add to 4. And 2 times 2 is 4. So in order to make this factor into this nice perfect square, y plus 2 squared, that's got to be a 4. So if I add 4 to the left side, also got to add 4 to the right. And now we can reduce this right side or simplify and get 8x minus 24. So we're close to our final answer here. But the last thing we need to do is just factor out this term. So I can, nice conveniently, we can factor out that 8. We've got x minus 3. And I've got y plus 2 squared. And there we go. So that is our standard equation of our parabola. And real quickly, remember this is our vertex. This doesn't ask for this, but just for practice, the vertex would be at 3, negative 2, if you were asked to find that. And then because y is squared and our 4p is 8, we would know since 4p is 8, p would have to equal 2. So we'd go, because y is squared, we go 2 to the right to our focus, 2 to the left to our directrix, and we'd be good to go. All right. For this one, so first thing I notice, 2 squared terms. So it's not a parabola. And then we got to remember, okay, out of our squared terms, how do we identify circle versus ellipse versus hyperbola? Well, opposite signs means hyperbola. Okay, so opposite signs, hyperbola. So this is our hyperbola. Okay, so now we got to complete the square for both of these, because that's what we got to do with hyperbola. We got to get it looking like, since x is our positive term, we're going to have x something squared written first over something minus y something squared over something equals 1. That's our goal now, to get it looking like this. All right, here we go. First thing we do, group our x's first. So 9x squared and minus 54x. I'm going to group them and factor out the 9. So I'm going to have 9, well, let's do that in the second step. So 9x squared minus 54x, that's first. Then we've got negative minus 4y squared minus 40y. That's written second. We can go ahead and add the 55 over to the right side too. So we say equals 55. Those cancel when you add 55 to each side. Okay, so notice we have coefficients for both of these terms. And whenever you have terms like that, you have to factor them out before completing the square in order to get it to look like this. Otherwise, it'll be like 3x times something and 3x times something, which is not what we want for our final answer. So that's why you got to factor out that 9. So factor out the 9, and we got x squared minus 9 times 6 is 54, so it's going to be 6x plus blank. Okay, and we're going to add something to the right side as well. So we already had our 55 over here, and we're going to say plus blank. And what is it that we're going to add? Well, remember we want this to factor into x something squared, so it's going to be x minus 3 squared, since that's what two numbers add to negative 2. So I've got 9 times x minus 3 squared, but in order for it to do that, this has to be a 9. So 9 times 9 is 81. So I'm adding 81 to each side by putting that 9 there. All right. Got to factor out my negative 4. So I got to take out my negative 4 here, and I got y squared plus 10y plus blank. So I'm going to add something to each side again. Again, 5 and 5 add to 10, but 5 times 5 is 25, so it's going to be 25, and it's negative 4 times 25, so it's actually minus 100. So it's not plus anything, it's minus something, so it's minus 100. So 55 plus 81 minus 100, all of that simplifies to 136 minus 100, or 36. Get a nice perfect square over there, which is nice. And then the whole point of all this was so that this factors. So we've got minus 4 times, remember the point of this was it factors into y plus 5 squared. All right, so we're nearly there. Kind of like that last step of the ellipse problem. The only thing we have to do left is divide everything by 36 and reduce. Reduce our coefficients. So 9 over 36 is 1 over 4, and this is x minus 3 squared. And then 4 over 36 is 1 over 9, so the 9 stays down in the denominator there, and I've got y plus 5 squared. And that right there is my final answer for our equation of a hyperbola. All right. Now this last one here, notice we have both squared terms, same coefficient of 1. Doesn't have to be 1, but it could be something else theoretically. But they have the same coefficient, so they are circles. And here we go. So now we're going to complete the square for both of these. So I've got x squared minus 4x plus blank plus, now my y's I wrote together as well. They're already written together. Y squared plus 10y plus blank equals, add this 9 over. So we've got 9 on the right side. And I'm going to add 2 different blanks over here because we got to follow those properties of equality. Add to the left, got to add to the right as well. Keep the equation true. All right, so I've got x squared minus 4x. So we want this to factor into a perfect square. Remember, it's -2 and -2 that add to this. But -2 times -2 is 4, so that's going to be a 4. So we add 4 on each side there. And then I've got y squared plus 10y plus blank. So that's going to be 25. It's 5 and 5, add to 10, but they multiply to 25. So we add 25 there. So we end up with 2 nice, perfectly factorable trinomials. This one factors into x minus 2 times x minus 2, which of course I want to express as x minus 2 squared. This one factors into y plus 5 times y plus 5, which of course I'm going to express as y plus 5 squared. And over here on the right side, we've got 9 plus 13 plus 25, which is a nice even 38. And you might be thinking, oh, 38, it's not a perfect square. But that's okay, because all we're looking for is the standard equation of the circle. And while our radius would be the square root of 38, you weren't tasked with graphing this, so you wouldn't need to estimate where those points are on the graph. So it would be a little more than 6 in every direction from our center of 2, -5. 2, -5. So center of 2, -5, radius of the square root of 38. Okay. Now I'm going to identify and graph each of the following conic sections, which I'm going to do in a second review video. So cutting this in half, end of the first chapter 9 test review right here.